Welcome back to The Explainer. Okay, so close your eyes for just a second and picture a massive, state-of-the-art AI data center. You know the kind. You're completely surrounded by the hum of thousands of GPUs. They're processing billions of parameters, just absolutely chugging through immense amounts of electricity. It's literally a fortress of raw computational power. Now, open your eyes and look down at the smartphone in your hand. The gap between that sprawling, massive data center and the little device in your pocket, that represents one of the tech industry's absolute biggest engineering mysteries. I mean, how exactly can a tiny AI, something small enough to run on a phone, become almost as smart as a giant trillion-parameter model? Well, today we're going to uncover the hidden mechanism that actually makes this possible. So, let's dive right into this. Think about this completely impossible paradox for a minute. What if every single smartphone on the planet actually required a cutting-edge, trillion-parameter AI just to run its daily tasks? You wouldn't just need a bigger battery. You would literally need a personal power plant in your backpack. It's an insurmountable physical and thermal barrier. We all want the brilliance of these frontier AI systems everywhere, right? But we simply cannot brute force our way there by shoving server racks into our pockets.
Just consider the sheer math here for a moment. 1 trillion. The absolute largest frontier models out there contain roughly 1 trillion parameters, sometimes even more. And because of that, they demand massive data centers, incredibly vast cooling systems, and megawatts of electricity just to function effectively. And look, they are spectacular at what they do, no doubt, but their sheer size makes them entirely impractical for local, everyday edge devices. So the big question is, if we can't shrink the hardware, how do we shrink the intelligence?
Well, the answer is actually a massive paradigm shift within the AI industry. These giant frontier models, they have a new hidden job. They aren't just being used to answer human questions or write our emails or generate lines of code anymore. Instead, all of that vast intelligence is being repurposed for something much, much more profound. They're being used to teach smaller AIs. Basically, the giant models have become the educators for the next generation of artificial intelligence.
And that brings us to the formal definition of this engineering secret. It's a concept called knowledge distillation. This is essentially the process where a huge, pre-trained teacher model transfers its learned representations and its reasoning behavior to a much smaller student model. It is absolutely the industry's critical mechanism for getting around that brute force scaling problem we talked about. Because instead of training a small model completely from scratch on raw, unstructured web data, which takes forever and honestly yields pretty limited results, we use the highly refined mind of the big AI to actively mentor the smaller one.
So how does this actually play out? Picture a pipeline of glowing knowledge flowing step by step from a massive neural network directly into a compact one. First, the teacher model receives a prompt. Second, it doesn't just spit out an answer, it actually produces its internal reasoning and probability distributions. Third, that output is transformed into highly curated synthetic training data. And finally, the student model ingests this data, absorbing the deep patterns and internal logic of the teacher. And step by step, the student's performance rapidly catches up to the teacher's.
Now, this brilliantly illustrates why this particular method is just so incredibly effective. We have to compare what we call hard labels to soft targets. Think of hard labels like a really rigid textbook. The model is simply told an answer is either 100% correct or 100% incorrect. Very binary, right? But soft targets? That is like learning from an expert mentor. The teacher model provides probability distributions and reasoning traces. It literally shows its work, revealing how confident it is across a whole range of different possibilities.
Let's look at how those soft targets work in action. To put it into perspective, imagine the AI is trying to predict the capital of France. A hard label just tells it Paris. Boom, done. But a teacher model using soft targets, it might output a distribution saying 92% Paris, 5% Lyon, and 3% France. Now that tiny 5% probability for Lyon might seem like a mistake, but it's actually a goldmine. It gives the student model vital semantic clues about geography. It teaches the student that Lyon is related to Paris in a way that, say, the word moon or sandwich definitely is not. A simple hard label completely hides all of that rich context.
This hidden wisdom actually has a deeply evocative name in the research community. AI pioneers coined it dark knowledge. It sounds like something from a sci-fi movie, right? But it just refers to those nuanced semantic relationships that are entirely lost in conventional, flat training methods. By absorbing this dark knowledge, the student model learns the actual structure of the world, how concepts relate to one another, and that allows it to learn so much faster and achieve much higher accuracy than if it were just trained entirely from scratch.
All right, let's move into distillation traps and look at the risks of actually copying a mind.
Because, as you might guess, copying a digital mind is incredibly complex, and it definitely doesn't always go smoothly. When the student misunderstands the teacher, it falls into what researchers call distillation traps. Research in the ACL anthology highlights a few specific traps that can corrupt the training signal. First, we've got tail noise. This is where the teacher's low-probability guesses completely overwhelm the student, which results in overconfident hallucinations. Then there's off-policy instability, which can literally cause the student's ability to self-correct to totally collapse. And finally, teacher error. If the teacher makes a mistake, the student doesn't just blindly copy it. It might actually degrade its own local decoding abilities, just trying to make sense of a completely flawed reasoning path.
And just to show you how serious this can be, a recent archive paper studying medical AI models uncovered a pretty shocking finding. You would naturally think that copying a safe teacher perfectly would make the student safe too, right? Well, actually, researchers found that as the student copies the teacher more accurately, moving from baseline fidelity to high fidelity, it can actually amplify misalignment. In this specific study, the safety violation rate jumped from 76% up to 86%. When refusal behaviors aren't perfectly captured in the training data, a richer, closer imitation of the teacher can actually erode the student's ethical safeguards. Wild, right? So because of these risks, scientists are exploring an incredible new concept, basically a calibration knob for distillability. This is the difference between distillable and undistillable AI. Researchers have figured out how to use reinforcement fine-tuning to mathematically control whether a teacher model can even be copied at all. They can deliberately engineer a teacher to either smoothly pass its knowledge down or aggressively resist any attempt to be cloned.
And the crucial point here is that those exact same distillation traps we were just talking about, they can be weaponized for security. By intentionally making a model undistillable, developers can actively defend against unauthorized knowledge extraction. They are essentially taking those traps and turning them into active guards. This has massive implications for protecting model intellectual property. A company can deploy a super powerful AI teacher out into the world, knowing full well that an adversary can't just easily siphon off its dark knowledge to train a cheap competitor.
Which brings us to our final section, the future of edge AI, and seeing intelligence everywhere. Once we fully master this knowledge transfer, we finally step out of the massive data center and bring artificial intelligence directly into the physical world around us. And we are already seeing brilliant examples of this. Take Tiny Llama, for instance. It's an ultra-efficient student model with just 1.1 billion parameters. But because of how it was trained, on an unusually large corpus of roughly 1 trillion tokens, using these advanced efficiency principles, it punches way above its weight class. It relies on the absolute quality of its representation rather than just endlessly growing its parameter count. And this leads us directly to a very tangible future. Because of knowledge distillation, we're going to have smartphones that can execute complex logic locally, completely on-device, without ever pinging the cloud. We'll have autonomous cars processing sensor data instantly with zero latency. Enterprise copilots will be able to run locally on secure servers, meaning total data privacy is preserved. We're moving toward a world of ambient, always-on intelligence, where millions of specialized student models are just running quietly in the background of our everyday lives.
So, wrapping up the explainer today, what should you really take away from all this? First, intelligence can be transferred. It absolutely doesn't have to be brute force from scratch every single time. Second, by absorbing a teacher's dark knowledge, these smaller models don't need to relearn the foundational rules of the universe. And third, the future of the AI industry isn't just about building one massive, godlike model. It's an ecosystem. It's millions of tiny, highly specialized students, all continually educated by a handful of impossibly powerful teachers. Which honestly leaves us with a truly fascinating realization. We've spent centuries perfecting the art of human education. But as we sit back and look at how efficiently and rapidly these artificial neural networks transfer their deep, hidden reasoning to one another, it becomes pretty clear. The greatest teachers in the future, they might not be human.